Alright, so we could do this using calculus with a definite integral, or we could just use area, basic area. Now, for number 2, geometry is not going to work for us. How do we set this one up? Definite integral from 0 to 3, right? Area under the curve from 0 to 3, that's where the shaded region is, of our function x squared dx. So we can evaluate this, do the antiderivative of x squared, that's going to be 1/3 x cubed, and then we're evaluating that from 0 to 3. So that's 1/3 times 3 cubed minus 1/3 times 0 cubed. Well, the second part cancels out. So really all it is 1/3 times 3 cubed. 3 cubed is 27 times 1/3 gives us 9. Don't forget, we also learned last week how to do this on our calculator. So if we did math 9, that evaluates the definite integral. And newer calculators are a little bit nicer than mine. You actually see a definite integral. But for this one, I would type in the function x squared, comma x, because that's what we're doing the antiderivative in terms of. So that's kind of like my dx, comma 0, comma 3, and then it would evaluate that definite integral for me. Well, how about number 3? Anybody think they got the answer for that one? I'm hearing a lot of mumbling out there. Subtract the first 2. Right? Look at this. If we take this triangle and use a little computer magic, and then we end up with this little region right here. You don't have that feature on your note sheet? I'm sorry. Alright, and do a little bit more computer magic. Right, that's that region. So if we take this area of the triangle minus the area under this parabola, we're going to get that area of the shaded region in part 3. So 13.5 minus 9, we get 4.5. So this kind of goes back to geometry when you guys had some of those problems, find the area of the shaded region, or you might have like a circle inside of a square. You'd have to find the area of the square, subtract the area of the circle, right? Area of the bigger portion minus the area of the smaller portion. Well, that's kind of what we're looking at today. So that kind of leads us into theorem 5.1. If we have a function f of x that's greater than or equal to g of x, so this one's kind of the bigger one. This one's the smaller one. For every x in an interval from a to b, then the area of the region bounded by f, g, those two functions, and the line x equals a and x equals b is equal to a little formula we're going to come up with here. So this includes x equals a, x equals b. So that would be just the vertical lines right here. So in this kind of general example, the area we're looking at, well, that would be this region right here. Right, the area between those two curves, and that's what we're focusing on in this section. Area between curves. Up until now, we've just done the area under a curve, right, between the curve and the x-axis. But here, it's between two different curves. Well, in this case, f of x, that's our top function. That's the one that's bigger than the other one all the time, right? This curve is above this one, that whole shaded region. It really doesn't matter if it ends up going lower than it anywhere else, but in this region that we're finding the area, it's the top function. It's above the other one. And then our g of x is our bottom function. Well, kind of like what we did up here, to figure out the area of that yellow shaded region, we would basically have to take the area under the top function, so the area would be the definite integral from a to b of f of x dx. That would give us the area, basically, of this blue region. So if we went, well, take that back, that's not going to be blue with yellow and blue. But if we did this blue region right here, That's this area, right? But then if we go ahead and subtract the area under the curve from a to b of g of x dx, well then we're taking away this area right here. Right? That's the area under g of x. So if we subtract that, we're left with this portion right here. But we can simplify this a little bit. Instead of like finding the areas separately and then subtracting them, we can do it all at once. With properties of integrals, if we have these two definite integrals that are going from a to b, they're going to have the same upper and lower limits, and we're subtracting them, we can subtract them inside the same definite integral. Alright, so this is how we find the area between two curves. Take the definite integral from a to b of f of x minus g of x. So we're taking the top function minus the bottom function. And in this case, a and b are kind of defined by vertical lines, but a lot of times it's going to be defined by where they intersect. But we'll look at that with some of our examples today.